more data available and where it's trendy, it's still going on, but not as buzz as big data, which is the main name of the track. But why is it linked? Oh, it's really not going. This is the PowerPoint? Okay, so I'm sorry about the display. It's not the same as on my computer or previous one. We'll see what is machine learning. It's really difficult to read. What? Yeah, I know. But it's difficult for me to read too. But so I won't read all of them like one by one. Actually, it's quite difficult to have like exact definition of what is machine learning. So I took it from various articles, Wikipedia or something, and they all have different like interpretation. But like you could see, so basically it's computer science about data, perform task, optimizing, it's a bit of everything. What is recurrent? And that's why it's here. It's basically about two things. So it's about algorithm, or way to perform, and data. That's why it's quite combined with big data. It's like, so you need a lot of data to apply machine learning. And so with the ongoing data, the data volume going on and on, now we can do more accurate things and more things that we could do before with basically the same algorithm. Most of those algorithms are there for 100 years, 200 years. Some of them are recent, but they already exist for a long time. But we can do more of them, more accurate things, because of this data that's really like spreading around. Why machine learning? So that's now we really go into, if I'm too fast or too slow or anything, or pop, or you have any question, don't hesitate. So why machine learning? So the first thing is like, we see that we try to, of course, be efficient. It's especially in companies. So we try to do two things: go faster or do more with less money. Basically, that's the world we are living in. And we don't like to do things that are redundant. So we don't like to do always the same small stuff. So that's the scope of industrialization in general. But so with AI, we can do more than before. Things more advanced or more specific than just this industrialization phase or process. So we'll try to do all those things that human can do, but make mistake or do less efficiently. This is the second point. So it's like basically computer go faster than us. There's no miracle. And something you can see in a lot of projects when they automate something is because there are errors when humans do it. We are bad at doing things all the time around. We get bored. And, it's normal. It's not but so this is really the thing. And then we try to guess things like pharmaceutics, or we always try to predict things that's been in human like since forever. And basically machines and algorithms are better at it because our imagination, our prediction, our intuition most of the time, because we can like make a parallel with intuition because it's some small facts, is nothing compared to a computer and algorithm having all the data, like all the history and all the data points. We will see that after. And of course, why? Because we are keeping more and more data. I won't give the details that you had probably in the 5 previous talk. There is more data around. We keep more about them, so we can do more with it. And we have more computing power, of course, which is aligned. And that's really, really true. Probably I've seen this or something similar into one of the other talks. There will be a lot of probably common points. So in 2012, which is already late in the computer history, there were 20 zettabytes. In 2014, 30% of the enterprise, so probably the one you're working on, at least 1 person on 3, have more than 1 petabyte. Yeah, okay, if you don't know, it's huge. And in 2020, it's going to be 1,000 that. So in 6 years, it's really spreading. And so this data is helping us because it's promise for us, for machine learning, data scientists, whatever you call it, to have these algorithms like tune and perform and give more results or more accurate results, depending on the goal you have. So yeah, that's just an introduction. After we'll see the details of it and you will play a bit. I'll have a quiz and stuff. It's going to be, but I'm going through every steps, and bear with me first with the story and the history. So yeah, I'll give a small introduction to the story, but really small. Who knows about bias theorem? No, nobody? So basically it's statistics, it's probability of an event based on some condition. It's really the base, so it's the probability of an event happening with the history behind it, just like shortcut. So it's really be useful because machine learning is of course a lot of statistics. So in 48 is the first time that we use data, a computer use data, external data, in the same process to calculate something. Alan Turing, you might know, so is the first, not the first, but he elaborated and made a full thesis and his work career on can we make machine things for us, like solve some problem or more advanced. In 51, this is a buzzword, the first neural network from MIT, which is one of the most famous university in the US, Massachusetts. So they decide to mimic the brain, basically, 51 already, so 68 years ago. And then there's the up and downs already. In 74, everybody thought like machine AI, because back then it was more AI than machine learning. It will be magic, we're going to solve everything. They had the impression they had a lot of computing power, so they kind of get funds everywhere. We'll try to solve a lot of problems. And the funding from the lot of, for all the enthusiasm, they failed a lot of projects, which is a recurrent story too. It happens too now. So it's kind of like the first down of AI. In 97, that you probably heard about it. So it's the first time that first time ever, a human was beaten by a machine at some game or whatever. That he was really trained, I mean, really special professional player. Back then, the best player in the world. The machine failed first, and then succeeded on second try. In 2006, there's also an important date, backpropagation, so it's like learning what he learns, it re-injects. It's like really a loop of learning instead of just set of instruction. I mean, instead of, then Hadoop, I think you had an introduction on Hadoop, no? Or you heard about it in some presentation, I guess. We will see a bit because I mean, you can do some parallel, so I will see a bit of a, so basically it's the distributed storage that I'm sure you saw with big data, so you cannot store all the data at one point, that's how it exploded. Now we can use a lot of machines instead of buying a super calculation machine, $1 million, whatever, or more for that nobody, I mean, a lot of companies cannot afford. Now they just distribute the power, so they buy a small, cheap machine, and they distribute the calculation. And so this distributed storage and processing existed for a long time, but democratized in 2008 with this project, which is Apache project. Okay, and DeepMind is the second version of the, no, just going to it can interpret, so it was like studying from the image, like a video games, and just from the pixel, because it didn't know anything about it, from the pixel and the evolution of the pixel, what was happening, it learned the full video games, or to play. Just like, this pixel, I mean, if you don't, it's okay, don't hesitate. I know it's end of the day for me too, I had a long day today especially, a lot of meetings, but so yeah, but we'll see about deep learning later. Hadoop history, you know what, we'll skip up. So yeah, so it's a project from Hadoop. It's there for a long time. It was not Hadoop first. I'll do, Mapreduce, ring some bells? No, not in, okay, good. We'll develop it too. So it developed Mapreduce, what's called Mapreduce, let's say, algorithm, which is like what I was describing. It's distributing the problem into smaller tasks, which is map. We call it map. So I map my problem to, but we'll see that after. And then reduce is like putting back together all the results from all the small machine. Because in the end, you still need a unified result. That's one problem you try to solve. So this algorithm was really democratized by this project. And okay, so you can see it's very long. It's there for long, and now it's I mean, it's improved and it's integrated in a lot of projects. Most of the data science or machine learning jobs you will see today will include some Hadoop or some Spark. I mean, there's two big projects, so it's you're gonna. And so yeah, so as I was saying, the V1 and the V2. So first, it was one of the first like democratized machine learning principle, let's say algorithm. It's really like you have a lot of computer, you have one, actually, and so it's there's two things, and you will divide the problem in two. But so you need two things for that. I will just, sorry. You need two things for that. You need to divide the calculation, so the process itself, and you need to divide the storage. So you have a problem with the big data, so a lot of volume, a lot of whatever, let's say millions of PDF or a lot of numbers. You have two problems. You need to read all of them, and I don't know, try to find some numbers inside them, like Panama Papers, for example. You know about Panama Papers, I guess. That's like common. So they were trying to find links between documents, which is really difficult, and numbers, and it's like, but this guy, through ops, is hiding between some companies, so you need to find first the company, then the ops, and then go through. So there's like million of papers, and then million of links possible inside, and entities to find and to link, and so on. So you cannot do that with like journalists couldn't never do that 15 years ago, because they will need to borrow the NASA supercomputers, which is unaffordable. But now they can just like, okay, you have a laptop, we have a small room with a couple of computers, which is thousands of euro, but it's like decent budget, let's say. We'll build everything together, you send this part in this machine, this part in this machine, we'll make all computer work overnight, all the small ones, and together, the day after, they will send the results, we'll put them together, and we'll find what we have. So this is really Mapreduce, and so you need two things. And big data is a lot of time about two things. It's the data processing and resource management, and then the storage. It's like to divide this big chunk of data into smaller parts that every computer can manage on its own. Even your own computer, you have some Tera, you could work. There's also a lot of projects for a long time, like for astronomy project or physics project, where you can compute, you can subscribe to the program, and your computer, when it's sleeping, is computing for the NASA, for example. No, you don't know this guy? Yeah, I see somebody knows. So it's the principle of distributed computing. There's a lot of resource power. You cannot afford always a big one, so you distribute it. So Hadoop was really, really helpful for that. So the first one was really Mapreduce, and now what they did, they just plugged in like space for other data processing frameworks. So basically the new algorithms just feed there too. They use the same principle, and they will use more advanced or different, depending on every kind of problem will have different algorithm for it, optimized or not. And so they just open it to plug the most common one inside. So what is the principle? So I was kind of trying to describe it in a rough way. But let's give an example. I mean, I gave the example of the Panama Papers, but so this is a text. No need to read the text. It's just like an example text. It's a sample text. One of the things, like if it's about text, it's not always about text. But if what I was trying to find is like, I have, let's say, it's again millions of papers. So that's just one page of one of the million PDF. There's like 100,000 million of them. What I will do is I will send on one computer, let's say, this sentence. And what I will ask him is like the most common word, or what the most used, and what's the vocabulary. So what we'll do, we will map it. So I'll do a representation of the phrase by word. I'm simplifying, but so this is simply the first sentence that is there, the beginning of the sentence that is there. So what I will do, I say that the word is, this is happening one, then I know is happening one. I will just count them. So you have the list of the word on the left as they appear, and on the right, I'm counting them. So it's just like, it's one of ways, it's like mapping. So this is for one text. And then I until there I will retrieve from all the computers all their summary computation. Again, it's a simple example. So if I combine all of them after, so from thousands of papers like this I did on one computer, I will basically have just a list of words and numbers. So it's already, smaller, and it's just kind of summary of what the words are present. Like if I want to know what are the topics, what is it talking about, then I will need typically this kind of stuff. So if a lot of if England or some country named a lot, I know that it's like one of the topic, and so on. And then reduce, I'll put them all together at the end. All those machines will send me the result at the end, and I will receive this is an example, and from another machine 2, and actually in total I could have put bigger number, but there were 2 this, 2 1, and then I have like a representation of not only one part, but then the full part when I put everything together. Is it okay for everybody? Don't hesitate. It's like principle. Okay? No? Seriously? Up? Good? First time I don't have question on this. So, no? Oh, good. I'm tired but clear. Let's start. So no, but so you got it. I don't think I need to explain this one. So I have a big stuff. I will divide it into smaller chunk. So I'll divide it into parts. This block can still be thousands of documents, right? Okay, everybody got it. Just like I'll divide it as much my smaller unit of computation. So one computer can handle. So one computer, let's say I know it can handle 1,000 of documents. Let's say. So every part would be 1,000 of documents. Example. Then I'll do the map, so I'll do the operation I need. It can be like finding the links in the Panama paper, it can be finding my vocabulary in the example I gave, and then I'll put all the summary, so everything you produce per documents, like the tables, I'll put it together. That's my useful data, because that's what I was searching in my world set in the beginning. I divided the problem, and then I copy the solution to local. I mean, I save the solution on my computer at the end. And basically, I mean, that's a simplified version of what Mapreduce is about, but I guess you understand, I mean, how much can be useful. I mean, just it's divide and conquer. I mean, in a typical war strategy, I will just divide in smaller problem that I know my soldier, I mean, my computer, small computer can handle, and then I'll put everything together at the end. And that's the simple principle. So that was the bit of history and introduction. Now we'll see still. So this is really clear for everybody? Okay, it's good. So yeah, so the types of machine learning. So now artificial intelligence is like solving a lot of problems. Machine learning is part of artificial intelligence, in case I was not clear, and we'll see that after. But so yeah, so what we call artificial intelligence basically is, as you can see, machine learning exists for a long time. So artificial intelligence is basically machine learning most of the time, and then since more recently, and it's also like, I like history a bit, but so what you call it's specialized in artificial machine learning, and then now we have deep learning, because we have more. For deep learning, you need a lot of processing power. It's like I will try to explain in understandable words what is it about. I mean, what is the difference with machine learning later on the presentation? It's way, I mean, it's not only useful, but it's way more advanced and way more computation. It's really try to mimic the brain, I mean, differently. And so this coming from, it's really in boom and in use since 2010. But it's a subset of machine learning, which is a subset of artificial intelligence. Machine learning is like the main subset of it. And so in machine learning, you have three types of algorithm, of way to treat the data. So you have supervised, which is the less magic, let's say it like this. I will explain calmly. Then unsupervised, that means you don't have to do anything. I mean, you don't have to do anything. You always have to do something, but supervised means basically, as it's wrote, that a human has to supervise, like to interact in the process. Unsupervised means you basically run the algorithm data and will auto-discover. I mean, simplifying, but that's so it will be. And then reinforcement learning is like algorithms will learn to react to environments, like an algorithm to learn from these mistakes, let's say. So it's more like typical, it will be in the games. You will play something, you will see that it's not working, you will try something else. This is reinforced, so you learn from the past, so this reinforcement learning is less used, I mean, in business it's less used. It's not less useful, but the supervised and unsupervised are as the most. So unsupervised is data-driven. Do I have an example? No, I see I don't have an example. So unsupervised, typically, the difference is like we can do basically the same thing, like I was saying, like topic detection. So I have a text, which I don't know. I mean, I have a lot of text. I don't want to read it, and I would like to know what is it about. So it's called topic detection. So I'll have like like I'm doing, Lex, so it's a legal, like a legal Google, let's say. So it's, you can search around all the legal judgments, documents in Belgium, and I receive documents, but I don't want to read it to see if it's a judgment or if it's whatever, it's an amendment to a law, or so the machine, we're sending it to the machine, and automatically, kind of, it will say, from this vocabulary, from this phrasing, I know it's a judgment. So it will add the judgment tag, so if you search judgment, you can find it. We didn't know it was a judgment, specifically when we receive it, we're just tagging like this, using machine learning. We're using supervised, but I will explain just after. And then, so the two of them, that's what we call classification. I'm classifying one document into some category. Labeling. A lot of machine learning is about labeling, putting a tag or label into some data. Like, this is good or not, do I have to go left or right? It's like, always decision is basically putting good or bad or whatever. It's a lot of machine learning is about labeling information. And so the difference is, like, with supervised learning, like if I know, for example, in my case, that's why clustering will typically divide your data sets or your documents into categories, but you cannot choose the categories. You will say, there's this word is appearing a third of the time, 33% of the time, and there's I discovered that it's like a tag cloud, some words around this kind of domains, and you will make link automatically, but you will find it on its own. You will define like, I found this, so I'm classifying them like this. So you can make clusters. It's useful for clients, for client segmentation. It can automatically divide your clients into segments that are more useful than what the software or what your analyst will do, like, we'll say them from 1,000 to 2,000 revenue. Actually, it's like, what do you say, artificial. Maybe it's not good classification. The algorithm will say you the right, the optimal classification for your clients will be from there to there and so on. That's clustering. Supervised is, I will need to help him. Like, I want to know if the document is a judgment. The algorithm has no idea what is a judgment, how to classify it as a judgment. So what we'll do, we'll give him data. So I'll take a judgment, I'll say, the document, I'll tell him this is a judgment. And then I'll repeat it every tweet, and he will learn from this. It's machine learning. So you say, when he says it's a judgment, there's a lot of judge, court. You will find the common points between all those documents, but I need first to tell him all of this. Typically supervised learning. This happens a lot. But then when I did that on 1,000 documents for the next 1 million, most of the time there's still some errors if it's exceptional one document, but he will find it on his own. So basically that's why we were trying to tackle in the beginning, automation. Getting down something that is like annoying for me. I don't want to classify all those documents manually.
So on that specific example, who is doing the labeling at first?
Usually, it depends. I would say workers.
In your example with your...
Depends on your company. If they can hire workers, like they will do it. If it's a small company like I did it myself. Most of the team, or I hire students, typically student job. But if you want to be sure, depends, because some of them you can do by student. If it's like, is this judgment or stuff, he knows about it. Everybody, but if it's more advanced, like about, I don't know, some strategy about some companies, there's a lot of parameters. You'll have to have some specialists. Even me, if I'm not business aware of so it really depends on your use case. Basically, the golden rules is do it the cheapest you can. Every company will tell you, if you can hire a student for free to classify your documents, because it's easy to classify, they will hire students. If it's to, I don't know, find some specific clauses in some law that you try to, then you will need a lawyer probably to help you do it. And your classification will cost you more, but you need it. So it's a trade-off. But most of the time, yeah, it's really about money, like all the rest. Okay? And so there's two types of, slides, sorry. So, yeah, I cannot see, usually I can see the next one on my screen, and you have but not in this system that I didn't set up. So what is it's a good summary. So what is supervised learning? So it needs manual validation, part, labels, whatever. It's about classification or regression. What is regression? It's, so in supervised learning, there's two main, in every computer machine learning in general, there's two main categories. You either work about text or ensemble, like classification, or about prediction. So if I'm trying to predict the price of a house, I know it has 4 rooms, 100 meters square in this area, so I have parameters, and I want to predict the price. It will be about some charts, some regression. That will be regression, everything like predicting really numerical values. And everything that is dividing those data, so all the house, I want to see which the one are expensive or which the one with pool or something. One of a company I know here are analyzing satellite image to see which house have pool, have a swimming pool for some bank, whatever. I want to, and to see. There's like signe extérieur de richesse, we say in French. So it's like you have money probably if you have a pool. So you might be a good client. So you see how it goes. So for that, it's classification. You either have a pool or not. This is classification. If you try to then from that say how much they might have money for my product, that will be a regression. I will try to guess a value. It will be regression. Still okay for everybody? Good. And so the supervised learning, it will do what we will do, we will learn a function or learn some pattern, learn some goal by looking at input-output. So if I give you that, I want you this at output. I will give him train exam, machine learning really. I'll training example so he can do the one I did 1,000, he can do the next 9,000 on its own. Hopefully, if I do my job right. Okay? So this supervised learning, unsupervised learning. So summary, so there's no manual pre-validation. Is it clear? Clustering is sometimes a bit more complex about dividing the, no, it's okay? So it will group basically just, what it will do is like, it will recognize some patterns like this is similar, this is similar, this is similar. At some point you can say the only input I will give him in some algorithm is how many groups I want. Divide the data into 2 categories, into 3 categories, then he will find, and what he will do is like detect the similarities, regularities, input data, and develop patterns from it. It has some name. I'll try to not give you all the buzzword, the complicated words, try to be like English simple, but don't hesitate if there's something I mentioned that you don't know, just ask. And so so reinforcement learning is the third type. It's less common. You have less in enterprise. You use it to play with stock exchange too. It's also trial and error. So if I do this, it's more dangerous. People try to lost fortune if you don't know what you're doing. But so what we'll do, you'll act with something dynamic, interactive. So basically like a game, the 2 techniques we were talking before is about data set that is not moving. I have those documents, there's no interaction. It's like you can read it, you can call it an interaction, but nothing is changing in the data. My algorithm, if it goes into the data again, it will be the same data, right? Like the price of the house for last year or my millions of PDF of Panama papers, they're still the same document. If I run the algorithm again, they will be the same. There is no expected change. If it's a game or stock exchange or what could it be there? We have example after. Then every time I'm trying, everything change. Everything no, but a lot of things have changed. Like the price of the stock exchange or the game where is and so on. So there's no teaching of, I won't tell him exactly, I want you to finish the game. It's not possible. So what he will do is like if you have Mario Bros, he has, basically when you see a game, like everybody know Mario Bros or any kind of those platform. So you have grass and then a hole, which is black on the screen. And so he will make the small Mario advance, and then for him, he doesn't know that black is a hole, but he will see that if he goes over black, he will try and he will fail. So he'll try something different. When it's black, I have to jump. He will try other combination, and he will see that jumping is working. And this, it's simplifying, and so I'll give him some points. When you reach further, you get some points. Go on.
Yeah, but do you need to tell the computer to jump then? That he's able to jump?
No, you have to give him the options. So you have, like Mario, I don't know, you have turbo, but let's skip it for now. So you have left, right, down, I guess, and then jump. And so he will try basically all possibility. No, until it's good, it's continuing the same. So he'll try something, and then, what I tried is not working. You tell him somehow, and then he will try something else, and you remember. And you try again. It's not just a simple try and error. It's not a simple one. It's just like, I'll try something else. No, you try to understand. It's still artificial intelligence. So you say, I failed. This is not working. What was the difference? I mean, you will. It was black there. I mean, you will try to. That's why I said pixel before. Yeah, but the context was different. When it's like this, I cannot do that, and so it's all. This is typically. This is the one. This is a simple technique they use to play Go or the chess stuff. Is typically this. I'll try this. No, if these pawns are around me, it's not. I mean, I'm dead. Whatever. It's like really. It's trying to learn from the context. So we'll try to avoid this situation. And then that's how he sees, okay, if I do this, the possibility of reacting from the opponent will be this, and on one of them I'm dead. And you will try to play for, and human typically can play 2, 3, professional 5, 10 times, and with this, when he knows all the possibility, he can, play 10, 20 moves in advance, and it starts to be complicated to beat. I mean, with the current algorithm. But so they're really that's really the principle. Still okay for everybody? You're so calm today. No question, one voice. I heard one voice. So yeah, so basically you can summarize it like this. So we call it agent and you can multiply the agents. Like if I play stock market, I can use reinforcement learning, a lot of small programs competing against each other. And so it's another way to do it. This one did this and he has more money. And so I gave him some points, and then they will try to, it's like emulation. So in general, even if you have only one, let's say my common example, it's called an agent, so it's more robots, basically. We like robots in AI, don't ask me why. It's always called. So you'll do some action. As I was saying, it will be dependent on environment, of the reaction of the around him, what he received as an answer, as a feedback from the action he made. He will observe the result, and either I give him a reward, he'll get some points, like the summary of the words, this, he gets some points, or he try to interpret, or he give him state like dead or whatever, bad thing, and he will try another action. And it's just like, or he go on if it was working. That's reinforcement learning. So I enforced my way and I basically grow my knowledge, but differently than from the true previous one. So this is the test I'm asking you at the end. You have to know all of it. So no, but I try to find a clear one. I didn't do it myself. Let's be honest. But this one was clear because you can see really like machine learning is divided into things that you know now. So reinforcement learning, supervised, so the 3 main pole or branch. No problem. But the slides are available if you want. So you can go on, but I can give you a link with the slides. So in unsupervised learning, as you saw, there is like clustering, like I said, customer segmentation. I don't know if anybody works in marketing. No? Yes? Behind. Target marketing, so to know, targets, whatever. Recommender system. Anybody use Spotify? Playlist of the day. Clustering. You try to make similarities. It doesn't have. There's no human validating. Oh, he likes this. He will like this. No. Anyway, it will be stupid because they don't need it. It's like people who listen to this song have also this in their playlists. And I see that this other guy who had also, let's say, I don't know, Blur. This guy also had Blur. He also had the other song the same in the playlist. This new guy that has just come, listen to Blur. I will suggest him this other one. Just okay. That's recommender system.
So we are all in some specific cluster, and they
yeah.
give us music from the people who are in the same cluster as us.
Not especially on one cluster because you'll have one cluster per song basically. So you listen to one song, there will be all the songs associated to that song or that musician, and then the next song. Of course, if you listen to similar, all the cluster will be overlapping. There will be common thing in the cluster, but they can make a cluster. I mean, I will make. I don't know. I didn't program Spotify, but the way I will do it is will be one cluster per song, or at least per artist. Let's say per artist. So if you have an artist, this one, but I think that's where they're suggesting this one is this artist is similar. Then you know that the most famous song of this artist is this one, so you will suggest this one first. But okay.
They may do some cluster about what people like the people are in the cluster.
The
People are more pop music and such kind of music.
No, that they don't need a cluster. That's it's just tagged in your. They don't need cluster because you have your saved song. So it's like just in your database. You know, you have playlists. If you never made playlists on Spotify, they cannot suggest you anything. You have first to save songs. So this is not a cluster. It's just like what you. I mean, the playlist you build. You build one playlist. So I decide when you listen to your RF this morning, it's like I would like to listen to this, to this, to this. This is not a cluster. It's just you building a playlist, and then from this playlist they can see. They could also cluster people probably in good customer or less, but not because of songs. He spent €10, and I tried to sell him the physical album. He did it. You're in the good. You are in the probable to buy again cluster, but that's different. That's about. I mean, that's about targeted marketing. It's also clustering, but no. I mean, you could do it probably, but I don't. I mean, it's not. It's not mandatory. It's no use. I mean, there's no direct grain. The song is useful because then they can. Basically, it's retention. It's like the rest. They would like you to stay inside, because if you stay in Spotify and you use it a lot, you would like to keep it. If you listen to only one song a month, at the end of the month you'll say, why I pay €10, I think, to use Spotify. But if you discover new music, you stay longer, then you use it more, then you say, okay, this €10 is justified. It's just about that. Okay? Dimensionality reduction, I didn't give an example because it's a bit more, compression. Structure, it's a bit more, I mean, complicated to display, let's say. But it's a bit about the Mapreduce. I mean, it's a bit way to summarize. It's also unsupervised. You can do it unsupervised. Then you have supervised learning. There's a typo. Identity fraud detection. So typically it will be supervised. So this is good transaction, this is good transaction. You need to know what is good to know, like, this is weird transaction. It's coming from Bahamas, whatever. But I have to tell him, he cannot discover that Bahamas is a bad, I mean, you have to labelize it. But it's typical, fraud detection is used a lot in machine learning. I mean, they use a lot in machine learning. You have so many transactions, you cannot have people analyzing anymore. I mean, you know, it is all the transactions, so they try to basically do anomaly detection. It's not in there, but fraud detection is basically anomaly detection. There's something that's a bit weird. Diagnostic, customer retention, that's what I was, no, but that's not the one I was explaining. We can go on. Image classification, that's typical too. Is it a cat or is it a cookie? No, or is it a dog a cookie? You saw that one? No. Some dogs with, not everybody, some dog has stains, black stain, and they are brown. And in some images, it's really difficult to see if it's a cookie or a dog. And then there's an algorithm. You can check it on Google. And there's an algorithm trying. You give him a picture with this kind of dog, and it's telling you if it's a cookie or if it's a dog. But some of them, even for humans, it's really difficult. But yeah. So classification of image, but you have to tell him again. It's like again, it's labeling, but you have to tell him first. This is a label. This is a cookie. This is a cookie. This is for him to learn. So it's typically supervised learning. And then the regression. So regression, as I said, is more about prediction. So population growth, life expectancy, marketing forecasting, like the sale of a product. All of this will be about estimation, prediction, weather forecasting, everything about values, as I said, but we'll have a practical example after for that one. Actually, for 3 of them. Advertising, all of prediction, but we have an example. Okay? So, quiz, I was not lying. So no, only the first part, no, I could make a quiz for real. So when you want to ask yourself how much or how many, it's a number, as I said, so really it's like down to earth. It will be typically regression. Regression was supervised and supervised agent. Cenk. Thanks. Cenk is Polish. Which category is classification? Supervised. Yeah, it can be unsupervised, but typically it can be both. This is a tricky one. That's why I ask you. Because as I said, the cluster, you can divide the information. If it's classification, I want specific stuff, it will be supervised. If you just want him to divide it to 3, for example, he can do clustering. So he will group similar stuff together. It's also classification. It will be unsupervised. But OK, most of them supervised. Which group clustering? Ah, yeah, I put clustering. You are right then. Let's say classification is supervised, clustering is the unsupervised. So that's not clear. I could put something different. Is this weird? Anomaly detection? Unsupervised? No, I gave the supervised. He has to know if it's Bahamas that is bad. He has to know. I mean, you know, anomaly detection, you could do it. Yeah, again. OK, I accept. Because if it's about price of a house, and I can compute the average, I will have all the price. I can see that if there is 1 point here, the algorithm can say on its own that it's out of the common. It could be unsupervised. If it's fraud detection, I mean some specific stuff I want to detect, then it will be supervised. I'll redo this quiz after it. It's not clear. Which option should be taken? Recommendation system, Spotify, supervised and supervised.
Wait, which option should be taken?
So recommender, where is it? What did you say?
Yeah, unsupervised.
Unsupervised.
Supervised too.
Yeah, clustering. I say classification can always, you can supervise. No, I mean, Google is doing recommendation too. It's suggesting you something. There's no people validating all the websites in the world. It's not possible. So recommendation is basically suggesting something that he knows is similar from all the others people. So usually 99% of the time, the other way around, 99% of the time it will be unsupervised. Just like information. Okay, everybody, you can have other example. Any of you thinks about something you wants to know what kind of machine learning or artificial intelligence is? You have I mean, something you use every day and whatever, and you have a question about it? No? As we are in the examples? No? Nobody? Okay. Typical question we did. So, machine learning is about learning. So that's not a surprise. We will divide learning into 3 steps. Still searching for an example? I can see that. We can pause. I don't know. How long do you want to make first parse again? I mean, I don't know what you expect to have a pause, I guess. There was a pause last time. Which time usually we make the pause? Halfway. Yeah. OK. Long way to go then. No, kidding. OK, so just tell me if it's really too much. So learning is into 3 steps most of the time. I will try to represent my problem. Like it's not only about machine learning in big data, it's a lot about computing in general. So I have a problem like in my job every day that I would like to solve with data, let's say. So I'll try to weigh, OK, how can I mean, what data I need? What is the way I have to go? What data I need? What kind of algorithm? What kind of approach I have to do for the? So it's like what we call representation of the problem. I have to find like do I put things whatever in column in Excel? Or what will I do with it? I mean, what's the approach I will take for my problem I have today? Then we'll try to evaluate the complexity and the solution. I mean, I'll try to put something in place and I evaluate. And then when it's working, basically it's for machine learning, it's try and error all the time. So I'll try to, I have a problem at the beginning. The most common mistake is try to have the most perfect solution from the start, and then you spend months trying to have something, and then you have the first results. I mean, you have results, and then you realize, maybe it was not the right way. So the best way to do it is like short cycle. I will try something that is not really good first. I mean, I know it's not really good, but I'll try if it's giving me something, and then then maybe on the way, while processing the data the first time, you say, yeah, but there's this and this and this, so I think it was something else. It was another algorithm. I didn't take this into account, whatever. And so you will evaluate your results. Most of the time, you will go back and try, which you can call optimization. So you try to just like have better results from so I'll try to predict, let's say, a price of a house. At first, I will say, OK, I will just see what data I need, let's say the number of bedrooms. Usually it's more expensive when there are more bedrooms, right? So, and then I try to predict. I will say, OK, there's 4 bedrooms, I predict the price. And then that's your first, like, what I need is the number of bedroom, and my approach will be, I'll take into account the number of bedroom to try to predict the price of a house. And then you do it and you realize, yeah, but sometimes there are small bedrooms, sometimes there are big bedrooms. Maybe the meter square might be a better factor. Maybe a 50 meter square apartment, even if there's presumably 3 bedrooms inside, will be cheaper than a 100 meter square apartment, even if there are so 3 bedroom inside, right? So it's like, okay, I will use 2 parameters and I'll try. And then you say, but maybe the same in Schaerbeek or Smolenbeek will be cheaper than the one in Woluwe, if everybody's from Brussels, or in London will be more expensive than in Manchester, whatever. So I'll take the location and so you'll try to, so it's really about what you need as data, what you represent, represent your problem, you'll evaluate your solution, and then you try to optimize. If you try from the start and say, oh yeah, but I have all this data, and I want to use, I'll use the meter square, I'll use, I don't know, the brand of the entry door, if it's a expensive brand, sometimes they're stupid, it's really crazy way to do it. I think there might be a link, by the way, by the price of the entry door or the windows, you probably can make a link probably with the price of the apartment, whatever. So you can find a lot of crazy parameters. The only thing you have to do is better than the others, because in this kind of stuff, because you want to predict the price better than competition or better than whatever. So yeah. So this is about learning. So representation, you will define an hypothesis. That's really important in terms of let's say to get more mathematical way. You'll say, okay, my hypothesis is that, as I was saying, the number of bedroom, my first hypothesis has an impact on the price. It's a big impact on the price. Then I will evaluate. How can I evaluate? I'll try several tests, and I'll do what we call a scoring function. So I'll say, okay, what you will do is you will say, okay, they have the number of bedroom. So I'll develop a bit the example I was telling before. So there is 3 bedroom and it's the price, and then I see that there's 3 bedrooms in Woluwe and with a bigger apartments, and the price is far away from my first prediction. Because I will test it, I will check. So the first one is you do the evaluation, I test with real data. It's like, my prediction is this, and then you go to the ads, you go online or ImoWeb or whatever, you see, yeah, no, not really. I was far away from the price I predicted. So you will evaluate. So you can see if you had a good classification or regression, a model, let's say model, should be model, if you had a good model or if you had a bad model, or not so good, let's say less improvable model, way improvable or less improvable model. And then you think about what you should have, maybe a different algorithm, maybe it's not a regression, maybe it's something else. You try to change the parameters, so as I said, you will add other things, or you will tweak other, you will change the way. And your goal is this evaluation to be the best possible. So you'll do the whole step, and what you want is to be close as possible to the real price when you check the rest. Or you'll sell to your clients. The bank want to know, to give you hypothèque, want to know what will be the price in 10 years of the house, so they can give you a mortgage accordingly, and they come to you as a data scientist, say, okay, so we know the price today, we would like to know the price in 10 years. Of course, this is more difficult because you cannot verify it clearly, but so you will try different things and different solutions and look at the one that seems good. And what you will do, you will take that's the approach, you'll do the program reverse. I know the price today, but maybe I can find some house where I can find the price 10 years ago. So I don't say it will be the exact line from but so you will, yeah, it's clear for everybody? So I'll try to reverse, so I have to predict in 10 years. What I'll do, I'll use the price of today as the 10 years future of the price from 10 years ago. And I'll try to, from this price and all the parameters I can gather from this old data, again data, to try to predict the price of today. And so I'll sell that, and I'll apply this algorithm on the price of today, for example, plus a lot of things. Maybe some area back then were not so trendy, maybe UCLA was, and so on. So you have to, it's really a play. You can see it sometimes as a game, but it's really about logic but yeah. So this is the learning. This overall process, I was saying, so the first one is to collect data. So you're going to fetch the data, gather it, whatever you need, clean the data. This is underestimate it. It's like most of my time. I have a lot of data like these papers or this, we have a PDF, was set for my legal Google, but the PDF is an image. So what I have to do, the first thing is try to transfer this image into text, which is called OCR for the one we know. And then OCR is creating a lot of mistakes. It told you it was an accent, it was another letter, whatever. And so a lot of gathering, cleaning, and then doing again. So I have my clean data set to start with to really try to start. So this is really like the overall picture of the job of machine learning. So you'll fetch, clean, then prepare for it. You'll train a model, and then you evaluate the model. So train is like the test you're making. And then when, actually this, I mean I have it after, this is a loop of course, even all of this is a loop. They should be internal. Fetch, clean is not enough. Either I refetch, refetching is so downloading, grabbing, finding it. I might try to find it from another source to see if I can have more clear stuff, or I can try to clean it again if it's not good. I mean, every of those stuff are like loops. And then the final one is deploying to production. Like if I did my price from the future and so on, when I think I'm okay, I will deliver my results to the client. Or I'll put it on my website if I'm selling some service based on the my AI dependent. Spotify will put it to production. Oh, I'm happy with my recommender system now, and the suggested playlist will finally, the end step is use it, basically. Use it in commerce. So yeah, if you want to put it like in goal, like horizontally, but again, more, that's why I use the loop, sorry. So it's gathering data from various sources. Usually it's becoming more and more rare than like Panama Papers, you use only one source. Like for example, again, in my job, you have this judgments, but also, I have the judgments, but there's also the law. And in the judgments, they mention article of the law. So if I want to be complete and understand what it's about, I will have the judgments, but I will need the law too. And then the law is mentioning person or companies or so on, and I will try, so you'll try to have as much data as possible to understand the problem more. The more data I have about it, the more my machine will learn, will understand the underlying stuff. I will try to clean data to have homogeneities. I was clear, I think. You'll try to build a model, again, with the right ML for machine learning algorithm. You'll try to get insights, value, results, the right results from the model. And then, I think you had a track about data visualization, right? No? Not yet? That's maybe the last one? Okay, so I can expand. Bad for him. No, but so yeah, and try huge part, well, I'll see it in details now. Details in short. Huge part is visualizing too, because it's difficult. All of this, yeah. So this is typically what we call before statistician screen. But so yeah, if I want, when I see the numbers, like even like the vocabulary I had in the beginning, there's one to see the most common word of a text. A common way will be a tag cloud. Everybody know tag cloud? So like a blog or something, tag cloud. So you will have like the most common word in big and then around the small and so on. So this is typically a visualization for text layer. It's really useful for me. Because if I have to read this Excel file where this one, I will lose a lot of time. So part of a big part of it, and makes you gain a lot of time, is picking visualization. But apparently there's a track, so I want the right track, so to have like a summary of what you're doing. My algorithm is going really good or really bad, and you don't have to read all the numbers or check. It's just like, apparently it's fitting. All right, so of course, according to the problems you're trying to solve and the type of algorithm you'll try to have, if it's weather, gas trend, you have different type of visualization. Okay, that seems like, but I won't expand. So now, maybe after the first one I'll make a pause. So it was 6:30, yeah. So now we'll see a bit much more in details. I promise you it won't be too much complicated. It's really like some of those algorithms, the most basic one. Nobody wants to make a pause yet? Still okay? Okay. So we'll see three simple, not the most advanced, not deep learning or NLP or whatever. It's three that you might hear in the introduction to machine learning a lot, or on some papers or even some journal. So decision tree, which is this is the decision tree, which is kind of really useful to divide for classification or whatever, and quite easy to understand, let's say. Bias, what I was saying, so it's classification based on stats. There's really an example you use every day about it, and we will use it. This one less, and then linear regression, we will go back to the price of no, I will take another example, but so it's predicting something. So yeah, so again, it's in the slides if you want to read. So this is the modern version of all the algorithms that are like related to each other. I don't know all of them, it's impossible. I mean, yeah, maybe some PhD or some university professor, but so there's a lot of version of everything now. So trying to find the right one for your data and your problem starts to be really challenging. So what you do, like every job nowadays, even for me, specialize in one niche. So I said in this kind of problem, I have 5 main solutions and I know which one to use, but it's like, okay. So you see what we try to use to solve financial or modern problems every day. They are divided. I didn't again. It's an existing. I should put my source, but it's existing white paper 1. So they're divided in regression. That's the one we will see. Rule system, regularization, neural network we won't see. Ensemble is like clustering. Deep learning we will see later. Bayesian we will see 2. Decision tree, dimensionality reduction. Clustering. Ensemble. Random forest. Okay, this number clustering, and this another one. Okay, and instance-based, which is really common now, but it's really mathematical ones. So I try to put the ones that are easy to explain in English. I won't give you a maths course, I promise. So decision tree. Took a down-to-earth example, simple. So this is before reading the question, but probably you did already. So this is a simple table which I gather like some survey, let's say, survey results. I have gender, age, and their favorite app, okay? So I see that this female, 15, likes, what is this? Pokemon Go, I think. Then WhatsApp, Snapchat. Female, 25, so really like simplified problem, of course, to illustrate the problem. And so I will try to find rules, find patterns, that's what we say. So for this, I use classification, and I'll use decision tree. Let's say we use decision tree. We decided in our clever, educated machine learning background that we will use decision tree. So I want to see, not basically, classify or predict, but I want to see between gender and age, which is the parameter, which one seems more decisive for predicting which app will the user download. So you think it will be user or gender or age like this? So age? We'll see. Which we'll study the problem practically. So, might be it was age. So I realized that so it's not like this really in every problem. That it's not that obvious, let's say. But here I see that in my data, I see that if I cluster, divide it, everybody, I put 20, but should be maybe between 16 and 25. I don't know exactly the limit. I put 20, so I put the median between 16 and 25. The middle seems like fair limit. I see that if everybody below 20 is always using Pokemon Go in mind. So decision tree is like, if you're under 20, I know it's going to be Pokemon Go. Then I try to gather the rest. I don't know why I didn't put colors. So then the rest, let's use it and then do it. Then I see female. I'm lucky, females are using WhatsApp and the guy is using Snapchat, which is weird, but okay. I didn't put but so yeah, so if you can like really guess, you don't need machine learning for that, but that's an example I want everybody to understand. But so yeah, so the machine will do that over millions of column and parameter. So, and it will build you this decision tree to know which parameter are important and which are the factors that make people decide. And if you're marketers, for example, you use those factors. We are developing Pokemon Go, you can do then either way, we want to develop it for people above 20, so you'll do a target marketing campaign just for that because you realized it was not the case. I mean, you can do a lot of stuff, actions from this data when you're able, I mean, the machine learning summarize it for you. You might even, I mean, that's basically marketing targeting audience. That would be kind of this problem. So yeah, so then the simple, really simple, obvious decision tree will be like this. So this is decision tree. I'll try to, and what's important in decision tree is not so much, I mean, the end results, but how I divided, how my data set was, I mean, really divided. This, I mean, male, female was already in the data set because there's the only two options, but this, my aggregate, I mean, calculated. And this is important for me. So I know that I have to target, either I want to boost it or there's no need to target this audience because I'm not interested, whatever. I mean, it depends what you're trying to solve, but so it will give you all the parameters that are important for you. I mean, all not, but yeah. And one thing that I didn't say, which is important, decision trees are always binary. So we'll try always to divide two sides. I mean, in basic, okay? It's just like, I didn't say it, so prefer, but it's not that important. So yeah, so this was, where is it? Unsupervised learning. I didn't tell him which was the division first. I just asked him decision tree, target marketing, for example. I mean, there was no label to my example, but so yeah, I'll try to divide to understand my data set, basically. I want to say, okay, give me the insights, typically, of used for data analysts or marketers or something. So it will be this way. Classification, as I said, it's bias. You use it every day. Spam. Spam filtering, it's typically bias, so statistics-based. But we will do, I mean, really advanced statistics for some of them, Google, which is working really good right now. But okay, we'll use the most simple bias possible. Okay, I'll do the pause after this one. So, in your, I mean, you read again, and you see that those are spam. Let's say the algorithm doesn't exist, so you just put it yourself. You know that you open them, it's like, okay, and you, like, basic, like 10 years ago, yeah, send it to spam, okay? It's like, no, it's like basically automatic. I mean, most of the time it's correct, but it's like, okay, and you divided it on your own. Wrong side. And then you try to find patterns, again, you label and you realize that when it's using the word cheap, a lot of them are spam. Usually when they try to use cheap stuff, Viagra, but it's okay, you don't need, yeah, it's typical spam. It will, yeah, but it's in the example after. So let's say cheap, and I see, okay, so when I realized that cheap is like, some of them are valid. Some friends find me cheap hotel or trips, whatever. Some of them will be valid, but most of them are wrong. What I will do is like, okay, I'll say cheap. I'll put it there. How many percent of cheap emails are spam? Somebody can tell me? Approximately 4 on 5, all right? Every line, so 80%. Shouldn't have answered, but okay. So when you use cheap, 80%, there is an 80 basically. So what is Google doing is like, okay, we label them manually. The first, we had to try it, so it's supervised. I won't ask you the question, I promise. Supervised way is like, okay, we tag them, this is spam, or use people using them. Basically 10 years ago you were saying this is spam, and Google had them on their servers. They didn't do it on their own. They used you to do that for them. That's even cheaper than students, by the way. And say, most of the stuff, they then use topic detection or word stuff, like I was saying, this count of words, and then the one you sent manually for years before those algorithms were efficient, they use it as a training set, and it's like, and the common words are. So they combine two artificial machine learning technique. One is statistics, Bayesian, and the other is topic detection or clustering, whatever, and they identify the words that are the most common in those spam, or the words or the patterns when there is no sender, or the sender is yourself. I mean, they will try to find other things, and that's what they're doing. So this is typically Bayesian. They check that when there is no subject, 67% are spam, for example. Viagra, yeah, 99.9, I guess, hopefully. But yeah, so this is really simple example of Bayesian. They use stats about data sets to make some decision. Again, supervised, and in this one is spam. We can also anomaly detection, but diagnostics, no, not really. Okay, it's not in there, but it's classification. I'm classifying them even on the stuff are spam. Again, it's a label, as I was saying, bilateral, yes or no, good or bad. Again, typical machine learning example, spam, not spam. Okay, then we'll do the mathematical one, so I suggest we make a pause. It's 1 hour, 20 minutes already, almost, if we start yet, 35. So I suggest we make a pause here, and then we'll tackle the numerical problems. Okay, so okay, so the only one I don't have is dimensional reduction, as I said, but apparently we'll have some introduction later because he uses and he knows it. I'm curious about it. Or you want to do it now, maybe? I don't know. At the end? Okay. So we'll see regression. So, I mean, I picked the one I picked because they're really common, and I mean, in introduction and they're good examples, like this one example, all the, I mean, not reinforcement learning, but the most typical way. Typical spam is everyday stuff. I could use recommendation. I mean, clustering we did with a decision tree for like recommendation system, and then regression to evaluate. It's the only, I mean, the main numerical one, so I will do that one too, but I could have done PCA too. So yeah, so regression. Actually, last time I said I should have done houses again, but maybe we are already fed up of houses. So let's invent some funny problem, let's say. So we will try to predict the speed I'm running a 100-yard cache, everybody's running, according to the amount of YAM you consume. I found this example without the graph in a book, and I found it funny. So we did the, so I'm here, I'm not very fast, and I don't eat a lot of YAM, all right? So this is my first data point, not data set, so it's one data point. So let's say I receive a lot. I will, again, visualization is important. If I had all of them, this is typical, especially for regression. If I have all of them in an Excel file or whatever Tableau grid, it will be impossible, it will be difficult to know what is happening. I mean, I have to, you are human. If you visualize something, it's really a good summary in general. So I will use some graph. And so yeah, so I run some tests, I ask some people to eat some YAM and to run, some friends. And so I gather the results, and so this is the result. So this was me, as we said, and let's say this is you, not some friends, whatever. And we can see, we can predict, first prediction, remember the evaluation. So my first approach will be, it seems, conclusions, the more YAM they eat, it seems the more fast they run. I mean, like, really, like, basic stuff. So, what we'll do, linear regression will be basically linear because it's flat, and the regression because it will be, I'll try to basically draw the line, I mean, the algorithm will draw the line to fit basically the trend. So, and it will try, I mean, more points you use, it will move, but okay, so whatever. So here it's the line, I will put them in middle. Here it's easy, when there's a lot of points, might be more difficult, but I mean, less obvious, not more difficult. But here again, introduction, easy example. So yeah, so I'll draw this line, the black line, and I'll do it to show the trend or the pattern, let's say. It's more than pattern in this case than a trend. That they're running that fast for this. So all those data points are my like test set, I would say. No, my real set, my live set. So I draw all of them. I don't know why I put this one. Okay. We could say why I didn't draw the green line, which is logistic regression, which is another type of regression. It could work. Like, I have all those points. Why don't draw a line through all the points? Might be the right, I mean, why to try to have, like, I have small mistakes. I can see some errors. It's an approximation. I'm trying to approximate to summarize. I could have an exact fit. We'll see after why it's not always a good idea. Sometimes it is. So now, so I had my real data set. And then, so that's important. I will divide most of the time, and that's, we didn't say that before, that's why this example I'll develop a bit more. Part of the thing, so I have a lot of data, like my documents, especially in numerical. I will divide my data into real valid data, I mean real, let's say, the first data, the data set, and then I'll use test data. So I have all my data, I won't use all of it. I mean, depends. If there's new data incoming, I don't need to split them, but if it's like a fixed problem I'm trying to solve, there's no new, I don't expect new data about it, like the price of the last 10 years for the houses, it won't grow anymore, right? It's like it's finished today. I mean, if you define a project, so it's definite data set. I will divide, I won't use all the data to predict the model most of the time if it's a bad idea. I will randomly, and there's some technique to pick which point I will use, and I will say, let's say 80-20. So I'll build a model on 80% of the data, and then when I think I'm finished, I'll pull out of the drawer the 20%, I'll draw them, and I'll see if I could predict the 20% correctly from what I draw. Because of course, if I use all the data, I will model all the data. What I'm trying to do is guess something I don't know. I mean, or some new data that might be coming, here the future. So we always do this, and it's part really of the evaluation. If it's a good model or bad model, it's really common technique, test data, really important to keep this, to say, okay, I'm building a model, I have to find a way to test it. And of course, if I do all the data and I test it in the data I used, it will fit, because it's part of the data I used to build the model. So I randomly, to be sure that, of course, to not like randomly take, or randomly, there's something, take some data, I divide it, and I'll, so here what I'm doing, I keep the blue spots on the side. Logically, there are less of them, I mean, less than the data I use for the model. And then, so I'm trying to predict, and then I check with my test data. Oh, I think that's it. Let's see how it's fitting. Evaluation. I want to see if I need to optimize it still, or if I'm completely wrong, or I'm on the good way, I just need some more optimization. So I drew this. So okay, so maybe the green line was not so bad, the green line was not so bad, and I have some really good model. So this is the second step, to try to evaluate it. So I need data to evaluate it, because I need new data or something else to see, I mean, to make the disparity, to test it. I'll also need a way to evaluate my model. So that's a new problem. What is the way for me to calculate the error I'm making? If it's, or can I know just by drawing, calculating if the black line is better than the green line? I have to find a way to test it, I mean, to know it, to see which way I'm going to go. So, which is the scoring function? There was in the slides a bit before. So what I will do, I'll really calculate the error. So I take the first blue point. So I don't need the red points. I use the red point to build my model, okay? So now that the model is built, I kind of consumed, like ate those, because those data was used to build the model. They're gone, let's say, I'm not using them. I will just test with the data I put on the site to verify later if the model I built was correct. Now I'll try to see. So here, this is the parameter I know. To be really clear, I gave my friends or you some yam to eat, and then I ask you to run. So this is the parameter. I mean, this is the data, and what I want to predict is the speed. I could do it the other way, but I will draw the chart reverse. If you speed that fast, I can guess it's also possible, but it's not what I'm doing here. So yeah, so I draw it here, and this is my speed. I mean, this is the value of my speed. This is the value of my speed, but if I draw a line, that was the one from my line. So my model is this. It's there because basically, it's the value I was predicting. Okay. So if you ate this, so this guy, amount of yam, I predict that speed, and actually, he's running that fast. So I can measure my error. My error is about, I don't know, this is 10, 20 kilometers, so this is 19, 13, 6. I mean, approximately, quite 33% of error, approximately, which is a lot. I mean, for that speed, but or in absolute value, let's say 6. So this is my error. What I will do is I will do it for all my test data, okay? Whatever the algorithm I will run, I will always use, I want the same part of the data, this 80%, I will use always the same to try to predict my model. I don't need to tweak it, I have this data. And then this same 20% to test. Because then if I change algorithm, I can compare them. If I shuffle the data, say, okay, maybe my partitioning was not good, I have to retest all the algorithm I was trying. Is this my okay? But if I keep the same data and then the same test data for all improvement versions, whatever, I can compare them easily. I will do this, and what I will do is I will basically, the loss function, the error function is called loss, so my loss on the prediction. My loss function, here there are several ways to measure, they're all valid, different use case, but the most common one will be the sum of the error. What I will do, I will just compute for all my data sets, so here my test, don't correct me, my test set, I'll use all of them and then I'll make a sum. And that will be my error for this version of my algorithm, all right? Yeah, okay. So now my idea was to do the other one. Two, might this one be, this seems not that far, maybe this one is, not convinced? Maybe this one might be better, okay? Or maybe another line. I mean, the straight line was the one I draw was the best one possible. I mean, it's calculated. So I'm just trying something else. And what I will do, uneducated I am, I was told to measure the difference. So it seemed close, it seems close, but it's close from the graph. And it's one way to measure error, but in different problems. But actually what I'm measuring is my approximation. So actually this one seems like it's close from my line, but actually the mistake I'm doing is, I mean on the test part, is quite big. Because here is the first one, this is my first. And what I will do, as I say, don't get mistaken here. No, that's a good question actually. So I'm calculating the error from my black line, and then I will do the same. I'll sum all the errors for my green lines. So somebody can tell me why my green line seems way bigger and smaller here? Okay, because I didn't finish the calculation here. So here I have to add, so I did already, that's what I'm representing. I did the first three, so this one is this one, then this one, then this one, and I have to add the fourth one to compare to the black. I compare apples to apples, orange to orange. So I'll add this one here, okay, and my evaluation loss function will be, whoosh, seems a good idea, but not good, okay? That's my second version. And again, we go back to this evaluation, trials, okay. So I'll keep with a straight line. Seems like a good one. Then I will try something else. I know that the straight line is good, then I might try some other things, but okay. Okay, it's clear for everybody. So that's loss, evaluation function, whatever, scoring function. So it's a way to try to evaluate my model. So algorithm, we will call it model in machine learning or artificial intelligence, is the way I'm trying to model the data. So if I want simply to try to model the data, I will say they follow a line. Okay? That's, no? You can still stop me, ask me, because I will continue to build on this example. So if you, I didn't move. Okay, it's finished. Or not? Okay. Loss function, measuring error. Really clear for everybody? It seems like not totally convinced. Seriously, it's just we can. What is not clear? I can see in your face you're not completely sure. No? I can start again. I mean, I can try to find other words, no problem. So. I'm trying to, let's, maybe not the most practical, let's go back to the house part. Okay? So this is the prices of my houses, okay, that I use for my data set. And this is the price. Not this, just this scale, this Y scale is the price. And this is, let's say, the meter square to do the simple version, I mean the simplified version. So what I'm trying to guess is the price from the meter square of the house. If it's 100 meters square, it will be that price. If it's 140, it will be that price. So let's say it's linear. So that's all the house. I'll skip that green part for now. So my goal really is like to find a model. So it's this black line. So because I know this is my test. I mean my model data, the data I use for the model. What I really want to know if for some house I don't know, let's say here, or I receive from my company agencies like, oh, we have a house 120 meters square. How much you think we can sell it? So I'll need my model. There's no house in my data set 100 meters square. I'm just guessing it. I mean, exactly. I'm simplifying the problem. So they will give me some stuff, and I will give them a price. I think it's worth this. That's what I'm trying to do. That's my approach. That's my problem. All right? Let's see. So I'm using data points to try to guess a line, like what is the parameter, the meter square, how is it influencing my price? That's my problem. So you give me one data, and from this data you want me to, it will be a lot of data in practice. It will be, as I said, the number of rooms, the location. Of course, there's a lot of parameters for a house. So I took a simple example of the YAM. But so they will give me one set of data, not obvious. So they will give me, like I said, 4 rooms, Etterbake, 150 meters square, and year of build probably. If more recent house will be probably, if it's a recent house, whatever. They will give me that and they will ask me to calculate. So I'll use something like this. And so I say, okay. So I say, okay, the house you're asking me about, we don't have it. I mean, you don't have something exactly similar, but I can tell you it's this price. That's what I'm trying to do. So what I'm trying to do is from those points that are disparity, trying to find something that is real for every house, that I can guess for any house. I'll say, oh, it's this one. I can give you a price. Okay, so that's my approach. It's okay, I mean, I guess it's okay. So I'll try different way to do it. And if it's the data I receive, I could say, okay, but why I'm not doing this? Which is called, I don't lose the other ones, this is called overfitting. I'm overfitting, so I'm like really drawing my lines on the existing data. So I'm like trying to be too good, let's say. I'm overdoing. So I really try it's better to have a gross estimation most of the time than really trying to say, if I had too many parameters, it will be way more computation, and most of the time you don't gain anything. Whatever, it's called overfit. So I'm really trying to fit to my data points, called overfitting. It's a classical problem. When you are in school or you try to solve this kind of problem, you try to be as accurate as possible and to have all the parameters in question. And most of the time won't work. It's better to find the one that really make a difference. That's why I said maybe the number of bedrooms are making a difference. Part of this is finding we call it features, the attributes of the data. It's also a field of machine learning to find which attributes of my product or my data are influencing the most, correlating the most with what I'm trying to guess. We use PCA for that, by the way. To try to find which features. So that's another problem. Trying to find which columns in my Excel is the most relevant, let's say. They are the most impact on what I'm trying to guess, okay? So this is another problem. But so first you have to do this, which is a big problem, and then you try to use it as a modeling tool. Up. So, common mistake, as I said. Still on. No test data or bad test data, but that's more advanced. If you have not, common mistake. Fitting, I had it. Fitting training data well, like the green line, but not test data. So what I was doing, the way I did it was overfitting, but the name, I'll spare it to you, is bias variance trade-off, whatever. So when I'm trying to fit too much my training data, I not like to summarize, to try to find like a trend, but really too much, like it has to be that. It's this complicated word, don't remember it. And of course, the most common mistake is not picking the right algorithm to try to solve my problem. Supervised when I need unsupervised, or not the right regression. For example, most of the time it's, we do linear regression. For this one, which is common, can be logistic or logarithmic. For this one, it seems like it will be like this, right? So it won't be always. If I do linear, this time this line's not this one, because probably the test one are not good, but from this one I will draw something like this. If it's all the data, all right? It's okay for everybody? I mean, yeah, I'm in front of you, but so here I will do, this will be the command line, and this one probably because my test data for sure will be out, and then my error will be, will be bigger than the one that is, like say, the average. Basically, the simplistic way to do regressions, basically, I'm averaging all the, averaging the line in between of the points. Okay. Okay, good. Do I have a question on this kind of trick? Maybe not. Do you want to, because I'll go to deep learning now, so do you want to present or use you? You'll keep it for the question and answer session after, okay. Okay, so to go back on really like how to implement the day-to-day, what you will do in your company, or well, I don't know, whatever reason you came here. So you have some historical or gathering data, can be the market shares, whatever, market stock options. You will divide it, now we know, into a training set, training set, so it's the way I'm training my model, so it's like the learning set, let's say, to be training might be, so it's the learning or the model set, the one I will build my model on, it's called training set. I will model and build, then I'll do, as I said, train test loop. So I'll use the training set, I'll have my model, I will test it with the test set. Okay, so I build the model, then with my test set, I validate, test my model, predictions, if they're good or not. I'm doing that in a loop until I'm satisfied or until I'm out of budget. And okay, I said, I can predict the house with 82% accuracy. Most of the time, 80-something is already really good. I mean, for a house might be, but it depends on your problem. Let's be not stupid, but okay. So with some accuracy, then your business manager or whatever will decide if it's good enough to put it in production or what you want to do, or you take your own decision if you're building a product like Spotify. Is it good enough? Like for example, Spotify probably, if you have 82% of chance you like the users like the song, I will put it in the production. If the 80% he will listen to the next one, is really good. Above 50% is already, I will take the chance, all right? If it's some, land, some bank, and you're doing some loan calculation, 80% is like a big risk. 20% of risk that you will lose 100,000 euros, I wouldn't do. So that's another problem. It's another big part of the problem is the decision making about how good is it, but it's let's say some other talk. And then when it's done, let's take the Spotify example because then, I realize it's speaking to everybody. So when it's done, I have 82% satisfaction, let's say, on the stuff. I'll put it into my platform and stream, so I'll let the live users do it. And they will click on it and they will use it. They will use my model, all right? They will use my clusters for Spotify to make the prediction, and I predict that the next song they should play is this one, okay? So when all of this is, and that doesn't mean I have to stop. Most of the time, if I have a first version of my recommendation system, I have 60%, it's like, okay, I'll do a product of it. There's already more than 50% chance they might listen to the song and stay on the platform. It doesn't cost me anything, I'm just suggesting. Even if it's 60%, I'll put it into production. Again, depends on the context, but then I'll try to improve it more. Because if it's 80%, then I have my chance that my business is going well and so on, like every business. So it doesn't mean that when I put in production, I won't work on it anymore, but I have to define a threshold, a minimum level of satisfaction for my business problem. And then when I do this and I reach it, hopefully you reach it, because there's a lot of failure, of course, too. It might be you'll never reach it, but when you reach it, you put it in production. Okay, the scheme, this is business scheme. Yes? There's a lot of techniques about that. It's called subsampling. So you'll try to take a sample of your, most of the time, like if it's yearly data, it depends on your problem again. There's a lot of techniques. If it's yearly data, of course you won't divide and you work like historical data. And you have from, I don't know, 20 years, from 1998 to 2020, of course, if you take 1998 to 2015 and then you keep the last 3 years as this data, is probably not. So it really depends on the characteristic of your data. So here, and if there's region, you'll probably, it's part of the work, you don't know the results, but you'll work again on some features, like you have historical data about region and price of a house, again, and you will take, you will write a small program, I mean an algorithm that will say, okay, I'll keep 20% of data each year out, seems like a good logic, because price will have, okay, and approximately some of them in each region on the factors you define. Again, it's part, subsampling is a big problem, and it's part of the thing you have sometimes to try and error. You take some sample, and then when you evaluate your test, you think you have the right model, it's also part of it, and then you do your test, you're always far away from the prediction. Maybe your division was not good. And you'll do the same thing just by redividing your data set differently. Maybe I did something wrong. You're thinking about the problem again, or by the whole thing you see that other parameters were more important than the region, because you see it from from your result. And so you say, okay, I didn't take that into account to dividing. Then the problem, as I said, you'll have to evaluate all the algorithms that were not trash, that were quite a bit good. You have to evaluate them again, of course. So you have to keep everything that's part of the problem too, but okay. So, but with experience, I mean, depending on the algorithm, it's always the same. So it's either features, like for historical data, the year for sure will be, I mean, it's obvious. Things are evolving with according to the years, and so you will keep a bit of every year, then there will always be some obvious division in the data, and you'll try those first. And most of the time you'll have to do it, do the division again and run the test again. Yes. All right, clear?
Yeah. But it's kind of, after so many loops, it's kind of deterministic, the model that analyzes the output of that process, or is not?
What, say it again?
I mean, you try several subsets.
Yeah.
Training.
Yeah.
Few times.
No, a few times with different results. I mean, if you try it with the same data and the same algorithms, you'll have the same answer. Yeah. If it's regression, if it's reinforcement learning, I mean, the one learning, yes, but so that was not the question.
No, I think, okay, let's say from the creation part,
yeah,
the output is a model.
From this, yeah, yeah, so it will be either, if it's clustering, it will give me cluster of song, the model will be cluster of song or artist, let's simplify. So I don't know, Snoop Dogg is close to Tupac, whatever. I mean, there was just like a graph, let's say, classification. So all the things that are similarities, if it's regression, it will be a line or something. I mean, it will be some mathematical function giving you some lines. So this will be, yes, they will be, and so so yeah.
The question is, after all the different subsets of test data and training data,
Yeah.
there's so many loops.
Yeah.
My question is, if the model, after all, you can, if the model is always the same.
No, the model is not always the same. The model is not the same. Every time, so every time you will, up. Yeah, so this is my training data to use the same, so modeling data, this is the model I use. Let's say it was efficient, and this one is super simple. So my first model, because I picked this algorithm, is the same parameters and it's the same data. I mean, the parameters will be the angle of the line for the black one. There's one parameter, for example, and the second parameter will be like typical. I mean, if you do maths, so it's ax plus b. So the second parameter will be here. How high is it? So it will be 2 parameters. So what you will do is basically you will try to fit the black line the best, and you'll do it once like this, whatever, and then you'll turn it to your data, and you'll do your score function. You'll do the stuff, and so you'll have a result. Of course, if you run the same data to the same model, you'll have same results. No point. The second stuff to optimize is not to change. Either you change data because you were completely wrong, but that was like an exception. It was like the subsum that was answering. Most of the time, let's say you divided your data accordingly to model data set training, and then test set. What you will do is changing neither the parameter or the algorithm. So you'll try to find the right one, and then by changing those parameters, you will have different results in the error evaluation. Because if the line was like this, then all the distance to the lines are different. All right? I mean the second one. So if I do so this is two models. So what I will do is this basically every time. So I'm comparing. I don't have one with the two compared. No, on the same. No. Okay. Okay. So you have this black line that disappeared. I should have left it, which is this. And then you try another black line that is different a bit, or another algorithm, and it gives you another evaluation. And then you try again and say, no. Basically, the previous term was better. So I stay on this one, or either maybe I try different loop. I mean, you will try to find. They have some machine learning will suggest. I mean, the new stuff will suggest you something or calculate something, but you will try. That's the try and error you will do. You either change algorithm or change parameters in the algorithm to find the minimum error, the one that is predicting the most efficient way. Right? It was your question? Not really. Not completely. Half of it. So you just, I mean, if it's not disturbing anybody, you just go on. Just specify exactly. I mean, try to.
My question was more okay, can you go to the diagram of the
training?
Yeah.
This one? Yeah.
So you split it in test data and training data.
Yeah.
So we run the process, we have a model.
Yes. So push. No, okay, you can speak. I don't speak though. Okay, I'm losing my mic.
But I see in the last process where the flow goes from the test model predictions to the model training building, there is a loop.
Test model. Yes.
So even though that loops can loop.
Yeah, but here it's written. Yeah, okay, but the loop is wrongly done. So here I go back here because it's called model training building. This is training set. So this is only the data. It's not the process. That's the. So this is my from historical data. So it should be different shape. This is my model building. So this is the green line.
You adapt your model with the other flow, isn't it?
With the other flow?
So with the flow from the loop.
Yeah, no, because I'm doing this, then I'm redoing I'm keeping the same training set most of the time. So this is data, not process. So this is my division into data. This is my model building. Model building is either the black or the green. Let's simplify. So I'm doing the black, then that's B. Then I do the black, then I do this, and then it's not good. I go back to here to change to the green. Then I need to, of course, then I change. I go here, I redo model training building. So I do a different one. Yeah, and then it should be like this. I mean, then I retest on the new one. I retest on this one. I mean, I redo this, which is testing from this. I didn't do this chart, but maybe it's not the most clear. Yeah. No? Still no? Not sure. Okay, it's clear for everybody else?
You just do the model with the training set, and the test set is only used to verify that everything is okay at the end.
No, this I know he got it, but
Don't change anything to the model. It's
yeah.
just verify the
So basically, yeah. So I always use this data. Let's say it's defined. I always use this data. It's just the arrows that are disturbing you, from what I understand. So here I'm deciding which kind of algorithm let's say algorithm, not parameters. So I'll do this line or whatever. This is what I'm deciding here, which algorithm, which approach. I'll do this and I'll run it on my main data. I'm doing this basically. I'm running the thing I decide on my data, training data. I will have a model, so it's the same box, but it's not really clear. And then I'll use the test data through this model to get the prediction. Okay? And then I compare, and if it's not good, I'll go back here to change the parameters, change the parameters, run the model through this one, have the model, test it with test data, evaluating it. Is it better than last time? Yes, I'm on the good. I will change the parameters, not the algorithm. It's not good, I'll try another algorithm, build from this set. When the model is done, I'll try it with this set, test it, compare do the score function, check if it was better than before. Okay, did I lose only one? Is it clear for everybody else? Yes, yes, yes?
And then after several loops, you you realize that the tests are not improving and the predictions are not improving.
You hide from your manager.
That could be that the split between the training set and the test set is not good.
Yeah, most of the time it's the algorithm or the parameters, but it can be the test set, yes. Then,
If it's already all the parameters, it will improve when you change.
no, if you change it in the right way, maybe you're not changing the right parameters, maybe you don't find the right algorithm. As you say, there's a lot, as you saw, there's a lot of algorithms, and some algorithms have thousands of parameters, I mean, have infinite parameters. Here it's really, I take simple example, but when you have, let's say even an Excel, which is like more advanced than I have, but still not big data, so it's still like measurable by human, you have 100 columns. If you have to try variation on all of them, it will still, but if you did all of them and one algorithm and nothing changed, then maybe your approach, your division, or even your, I mean, it's like every job. Then you sit and you say, okay, what I got wrong? Maybe my definition, my hypothesis, because again, my hypothesis that I can solve my problem with this. Maybe your hypothesis is wrong. Maybe you define the problem wrongly, or you don't have the right data. That's why we keep, I mean, that's why big data is there. Sometimes you try first time to solve the problem, and you think it's the division, then you try the algorithm, but from this data, there's not enough data or diversity, or there's one parameter or one source missing, and the algorithm cannot find anything. So you will think about it later, it's like, okay, but maybe it's not converging. I mean, it's like everything is not going the right way. What I need, and you say, maybe you can go back. Maybe I'll ask my manager, I know I will need, I don't know, the country too, whatever. Just get me the country. That's why we build data lakes or stuff. That's why it's important. The more data we have, the more accurate. Then I'm sure I'm not missing something. Because there's the division, don't be scared about the division training set, test set. There's also machine learning algorithm doing that. So they will screen, I mean, analyze the whole data and say, okay, and they will build training and data set, test set for you. From this, it seems homogeneous. I do clustering, typically. They are similar. Okay, I'll send one in the training set, one in the data set. You can use machine learning to improve machine learning. All those clusters you can put together, and there's like the recommender system. The first one would be, as I said, recommending, but with Spotify, then you'll use marketing target that you're buying something, so they will buy you again. It's another one. And they will combine as much as possible because the machine is working for them. Okay? Is better? Okay, clear? Yeah, you always say yes, so I'm not asking you a question. You know a bit more of this, or?
I know the principle.
Okay. So no question? I didn't hear you yet.
No question. Again.
No question? Oh, I'll get a badge today. No question? No, or something you want to know that is not there? Not yet? Okay. And you? I didn't ask you neither. No, is everything okay? Everything okay. So, deep down, but it's going to be a summary. This deep learning, I know it's already late and you had all a big day, more than probably. It's going to be really like superfluous, like, yeah, like the really like top of deep learning in the next step, because it starts, and this, I mean, the problem with deep learning, it's like, don't say to anybody I say that, except it's on the video. It's like bias, it's statistics. I mean, it's based on, because it's mathematics, but really, really like advanced. I mean, it starts to be really, really advanced. To use deep learning, you can be just script kiddie, download some software and try. To develop algorithm about deep learning, usually you have a mathematical PhD. So the bias, I don't say I could have think about it on my own, but I mean, spam and stuff and persons, I mean, could be done. Deep learning starts to be really like, everybody heard about deep learning or CNN I made 1,000 steps. Convolutional network, réseau neural network, whatever, things like this. No, nobody. Okay, some you know. No, not even you. Wow, got some points. So deep learning is like this is more recent. You remember the first? I mean, when I divided, so there was artificial intelligence. Machine learning is a subset, but there was also the years there, which starts to be like useful in industry because again, it's old technology, but in around 90s, 95. And then now from 2010, more and more we use deep learning, like self-driving cars, deep learning. Image recognition, like really like where there's way more data than just Excel. I mean, not just those. I mean, not only it's not true, but you can solve really big data problem with machine learning. But if you use deep learning, let's say the other way, you need really a lot of data, way more even than machine learning. For deep learning to be accurate, you really need data lakes or a huge, huge volume of. But we will see why So what is the principle of deep learning? Deep learning, or neural networks, assimilated, not exactly the same, is trying to mimic the brain. So it's about cells, or we call neurons. And so they will gather input. They use multiplication kind of matrix. So if you did some matrix multiplication, it's not really beautiful, not really easy. So they will, like the neurons, they will go to, here's one. So you have the input, and they will like go from neurons, layers to layers. So they will divide, it's a bit Mapreduce, let's say, they will divide the problem in big blocks, then small blocks and smaller blocks to be the more accurate possible, okay? And they will try all the combinations, most of the time. So you need a lot of data, but you also need a lot of processing powers. That's why it's not easy for anybody. There's GPU computing now, like NVIDIA and stuff, you use GPU cards. I mean, you basically need still supercomputer to do deep learning, to build a model, to use it. When the model is built, like for driving cars, you don't need a supercomputer in every car, hopefully. And then they will be flat. The battery will be run out after 1 kilometer because of all the computation. The sun also another problem. So not, but to build the model, to know when to turn and so on in the run, super big. So yeah, so here it's called a shallow, so small one. So what we will do, we'll have an input layer. So it's all my parameters. I'll have one per parameters. I'll do what we call hidden layers. So it will be all the computation inside based on those parameters. And then I will define class of output. I might have a lot of parameters, again, like Mapreduce. But what I want to do at the end to know if it's yes or no, if it's this image is a dog or a cat, whatever, might be turn left or right, accelerate or brake. I mean, more than that, but so you need some actions. But usually the action at the end are not only 2, might be more, but way less than the inputs you need. You ask some decision about a lot of data. And what we will do, the most advanced layer here, you might have 3, 4, 5 layers, so 5 different type of computation inside. We'll see a bit more details, but not too much. So shallow here is because there's only one layer mixing the data, whatever. Again, just let's say mixing for now, and then to give the output. And every neurons will some algorithm will remember the computation they did last time, check if it's better or not, whatever. Okay. See, small example. Really simplified, not really representing what we will do with with deep learning, but so you get it. So the first thing is it's completely, as I said, numerical, completely mathematical. I mean, not, you could use it for text too, but most of the time it's about it's computing. It's even to compute. Let's say even to compute text, you have to transform text into numbers. Okay, so a lot of computation. So here I have data. I don't know if it's still it's quite thin. So I don't know. So it's Alice. What I will need, as it's multiplication mostly. And division and one. What I will need, first thing I will need is I need the data to be centered around 0. So it's a new problem. So, and why is that? Because if, let's say I have a name, so simple problem, not fitting. I have a name, I have a weight, and I have an 8, let's say something simple, I have an 8 and a gender. And I'm trying to guess the weight, okay? Not the most funny stuff, but okay, so I have a name, which I can guess the gender or not. I have an 8, it's not this one, I will explain you where those values come from, okay? And I'm trying to get the weight, all right? So the problem, and you will use computation. That's the only thing you'll use. Like say multiplication, okay? That's the only thing you need to know for now. So the problem is that let's say gender is, okay, good. It's 1 for girls and 0 for guys, all right? But it has to be zero-centered. But there's no reason in any models, I mean, I don't know beforehand, why the gender will have a less input, less important parameters, because then it's not like the regression, where I know that there were 3 big rooms, it's just a parameter. Here, I use the value of it. So here, the gender, there's no need, I will finish my sentence, then you know, that the 8 has way more power, weight like bias, than the gender, let's say for my data. So I'm 186, 87, then I have the name, then I have the number of pockets, whatever, and then it will be 3. Then if I multiply 186 by 3, 186 will be the deciding factor compared to somebody which is smaller. The smaller number will have a lesser impact than a big number in a multiplication, okay? So we use a simple technique. We will remove the average. So it's zero-centered. So that means the average person will have a 0 weight. It's the average. And then if you're taller than average, you have some value and you'll be lower than average. So I'm centering my data sets, cleaning, okay? So I will remove so I'm 186 or whatever. The average is 158, whatever. So my value will be 186 minus 188, 58, 28. So my value here will be 28. Bob is 25, for example. Bob. Minus 60, yeah, because it's in pounds. Okay, so it's in feet. Whatever, what is it? In inch? It's probably in inch, but okay. So I will do it zero-centered. So that means that together the value should be around 0. All the value combined should be 0. Then I will remove the variation, but okay, whatever. So this basically will have, as I said, it's difficult. This will have, will be centered about 0, and when I multiply, I will use some computation to try to guess. Sorry, I'm tired. It's not. I guess it's not clear, this one. You can ask question, but I don't know how to make it way more clear. So and here I will have basically, typically per node, simple computation. So might be multiplication or division. That's my model. It's what every node will do. Do I have an example of that? Well, not really clear. You can see something? So this is a 4-level. Okay, we'll do with image. So I don't know why we don't see it this time. Maybe it's the conversion to. Okay, so it's faces. Then it's part of the faces. So it's eyebrow, whatever. Then bigger part, ears, and then the full face. And I'm trying to guess if it's, let's say, women or men. So I'll use several layers working on different features, like for the age or the sets. And I will basically cut. What I will do is cut down. It's a woman. I don't know if you can see it. Don't I have better image there? Okay. So it's features. I said attributes. So it's like the size. So this is face. All right. So I will divide into small, and I will ask him with computation to understand, like the distance to the edge and to all the characteristics that he might fit. And what I'll do is recompose. I use small part, then he will learn from bigger part. Let's say like this. Then here you can recognize it's a nose, and I will tag it as a nose. And then you will know when you see a face which part is the nose, which part is the eyes. But I don't know how to put it. I don't know why I'm not clear today about it. Patterns of local contrast. I don't care. Face features, face, output layer. Okay. So I'll let's just say I'll divide my I'll divide my problem into smaller. I will try to learn from the smallest features possible. So really small calculation, I will put it to the average for image is more difficult. then I will put them together and try to do it with the bigger ones, and at the end it will tell me, it's difficult, I could do it in a mathematical way, but I guess it's not interesting for introduction, so yeah, so we use a lot of smaller calculation, let's say, together, and features to extract information from the image, and in this case, and try to guess at the end from those. So basically, let's say, you will see that, you will see that when there's white, so it's the nose, and there's the nose and the contrast will be big white, then here it will be black. You try to learn from the patterns. So we will, just with the mathematical stuff, you will analyze that the contrast, for example, in this one. So this is really white, then all of a sudden it's black, and it's green, it's according to some pattern that it will recognize, it will be a nose. Okay, from the calculation it's doing. So we will analyze every pixel from all this stuff, and you remember, so we will shoot all the layers. It's like, okay, one layer will be about the distance. So if there's two white with blue part, it's like average distance, and something that is white, like contrast, you can see that there's some level in the middle, it's a nose, and I can recognize it's a face. So it will basically divide all those features in small parts, try to recognize them, then combine them to try to learn, like with multiplication, this together with this, I know it's this, and then at the end we combine everything to know, is this a tree, is this a human, is this something, through all this computation. I guess, I won't ask you if it's clear because I guess it's not, but so that's the principle. The rest is just mathematics, so I mean, I could do it, but I don't see the point. So it gives you, like, let's say, a small overview. You might write me an email and I'll try to find a better example, because this I had it this time. Try to find a simple example of deep learning, but I guess there's some simpler ones out there. So sorry, is it okay still? Can go on? But it's okay. The part is using only computation from features to build bigger models, step by step. I mean, yeah, that's the main principle about deep learning. You will use all these layers, all this operation, the ones after the others, to learn from the small part, then make bigger assumption to solve the bigger problem in the end, or the output you want. Is it a face of a woman or a man, for example? And then they will see part of it here with deep learning. They will also have classified, unclassified, supervised, unsupervised. Here, for example, for face, like I was saying for the image, I will need to know. I mean, I will have to have data set and valuation set again at the end and say, okay, this was a man, this is a woman. I have to tell him in advance. So he will decompose the problem. So if it's a woman, usually the eyes are closer. I mean, he will do the computation to find features, to find patterns from my problems through only mathematics. So it can be the distance, can be, as I said, the contracts. Men will have a bigger nose, whatever. He doesn't know that, but he will see how it transcripts in the image. Or men have a bigger nose, not longer, whatever. So he will find the patterns. He knows this stuff. He will analyze the pixel, because the image is just about the data points he has is a pixel, and find patterns. When the nose are bigger, I mean, whatever. And then from this and the label data he had, and all the computation, he will do assumption. And why we use deep learning for that? Because of all the variations. If I have a simple model, I have simple parameters. Here, I mean, when you take a pictures, you have this feature on your phone. You have a picture and it tells you if it's a face or not. I mean, you have this face stuff. Then you have to use it. I mean, that's how it's built, because they analyze so many images to know all the characteristics of the face, and you can be turned, so the face, the eyes will be different. From the perspective, they will be smaller, but then the nose will be smaller too. So it's like, okay, this is a face. They can even tell you which angle you are, because of all the characteristics. So first, there will be some people tagging. I mean, say, this is a face. Doesn't need to know the angle, but this is the face. This face can be like this. And you will learn from all those features. So we divide the stuff like, this is coming from an image from a girl. It's really dividing stuff. And you will learn from it. But as you can guess, as millions images, if you want something accurate, you will do like this. You need tons, like not thousands, milliards of samples to be live on your camera to be able to say, that's a face. Most of the time, probably the eye, the camera could tell you if it's a guy or, a man or a woman. It's not useful for the camera, but It's part of the thing we learned. So they divide problem into smaller part, Mapreduce, it's the introduction. Try to learn patterns from, to learn from those, it's really like simplicity. And then combine with bigger ones to have different perspective. Like we combine bigger one, then he learns other things. Other parameters, like bigger distance, like the here and stuff. And then we combine abstract level of features. And we combine it with some, and then we will evaluate again, then same. Is it really a guy? I will check it and do it again. That's still machine learning. There's still artificial intelligence. This process will be the same. Okay, sorry. It's the most clear I can probably do with this. But as you could guess from what I'm saying, or imagine, let's say imagine. So with traditional machine learning, this performance, if you have like price of a house, let's say, you can try at some points to include 1,000 parameters or have more data. Still it's advanced algorithm, but the performance at some point will stale. It will be like, okay, whatever data you tell me with the simple decision tree, let's say, with simple algorithm, your performance will be capped. At some points you can do more data, at least the same kind of data. Maybe if you have a new parameters, it might change your problem. That's different, but with the same kind of data, you can give more data, you won't learn more. Once you know that the number of bedroom is useful. So with deep learning, there are so many lives, especially like for image or for driving, self-driving cars, there are so many cases possible. It's not like an Excel file house. The features are infinite, so the columns are infinite. There's so many different things that can happen. And still, like an exceptional, like some dogs is passing. You'll have video that, and your car has to brake. It's not a common, there's so many, a tree will fall from a storm. In real life, you have because deep learning is more solving real life problems, you have so many parameters that can arise, then the more you have, it will still learn. It's like in this movie, this small robot, this small human, whatever, this trying to learn from life. The humans we are now is from life of experience. And if you translate that into computer data or life experience, what we become now, it's infinite. It's a really huge amount of data. And with deep learning, we try to really recreate more artificial, intelligence. So we're trying really to take decision from more complex, let's say, more complex factor. So that's why, the problem is that it's trendy, of course. Deep learning seems, but first you need a lot of computing power, and then if you try to predict house, solve or do something at work, segmentation, you probably don't need deep learning. For deep learning, it will be expensive. The models are more difficult. You need some more expertise to do it. You need way more data, way more money, computing power. So the common mistake now is people going out of university. It's like, I will try deep learning on my problem. Yeah. Maybe it's the good one. Most of the time, it's better to start with this. At least start. Maybe after you can realize you need this, but it's like all problem. It's better to try small step first. So try to, and then see what you need. If it's not solving, maybe, but I wanted to do, maybe it's because you need more computing power, you need different approach. Deep learning is different types of algorithms, so maybe it's because you need more. All right, so that's maybe the full answer to your question. So we arrived to the end, promise. So for now, there's 3 stages of AI. We are in this stage, to be honest. So it's narrow AI, we call it narrow AI. So we take decision, it's not like human, still call it artificial intelligence. We take decision or we build model for specific task. Really something really specific. If I build a model to predict the price of a house, it won't even work if I try to predict the price of a boat or land, ground without, I'm trying to sell without house on it. Won't work. And if I try to make whatever my algorithm transfer, we call it transfer learning, is knowledge, it won't work. I'm trained my data set to solve some specific problem. It's still called machine learning, it's learning from the data and it's doing things that on its own, but it's still what we call narrow, it's solving one specific problem. Then you have transfer learning. So we start a bit, we are like to try to learn be able to in certain, like in some deep learning algorithms, to apply what we learn in some other fields. Like maybe if we change the parameters but keep the same model, maybe we can still use it. I mean, and then you have the one from the movies. We are not now, not far, not in 10 years. Just don't be scared. Super AI, which is basically they replicate humans or even smarter than humans because they have the computation power additionally. So we'll have a robot that can decide what he will learn. So basically here you learn English and then you want to learn French. You just like build a model, a robot that is learning English. So it will learn French on its own. It's already general AI. And here it's human AI. It's do whatever. Then it will do sports. I mean, it decide what it will learn. Basically, just deciding on its own is like already some next step, which we don't have now. So it's super AI. But to come back to a discussion we had, so we are starting here. I mean, we are making experiments. It's not there yet. But the narrow AI is solving a lot of problems from business right away, right now. The Spotify of the world, it was iTunes Music, and there was other player, Napster, before. AI is completely taking over. Uber is not going well, but the solution is still there. They use artificial intelligence to calculate the price, the location, and so on. They took the taxi by storm. And the AI is not in every business, but in most of the business, even legal. We have legal, so I'm doing AI for legal. We're trying, in the US, they try to predict if you can win the case or not, based on the document you have, because they search in the existing old judgments, which is not available in Belgium, for example, because judgments are not published, but in the US it is. So you have a whole history. It's like, okay, it's this case, in this topic, this kind of claim, 80% chance you will win. Good. So you just need the lawyer to be there and use the same arguments as the previous case. I mean, I'm exaggerating, but an AI will slightly take over, seriously. So it's not because I'm doing it, but it's a fact of the world. I'm just lucky to be there for a long time, before it was trendy. And deep learning is not my field, as you could see, to be honest. But so yeah, so I think it's for most of the business, and you can see now these startups. There are a lot of startups, small companies using AI, and they catch up on big companies because with AI they can replace a lot of humans. So it's the same for children, even education. I heard some talks. I mean, there's a lot of. I heard two things. One guy that was doing reinforcement learning and reinforcement transfer learning. They are doing agriculture. And so they build fields in every continent, 5 continents. And they're growing something. But they're growing something with robots. So there's a robot, so this kind of tray, like the things you, in the park, in the Luna Park, that you have to take the, yeah, okay. So they use this and they plant seeds all the way. And then, so they use 2 things. And then they take pictures. They have, so on these rails, they have picture of the plants, which can be whatever, cabbage. And every day, every minute, they take picture. And from the algorithm, they know if the plant is growing well or not. Oh, this stuff is yellow, not good. Replace. Next one. And then they have parameters, and they know that in one continent, I mean, one of the fields they built in one continent, there's humidity, there's sun, and they are different than the others. So this stuff is centralized, and they try, and they see how plants are reacting to all these parameters with deep learning. And then they make deduction and they try it with another one. And they achieved with that, and no human, but yeah, a lot of okay. No human, they achieve more productivity than what we do with without any product, just like this one, not worth to let it will die. I prefer to replace it after 1 week with a new seed that will produce something than something else, and so on, and optimize all this. I mean, automatize all this, automatize all this. They have better production more than with any product with humans and machines that we have now. So this is the future of, I mean, one example of agriculture. And of course, to answer a question that we had before, for this, they used children, I think, or students, to label, to know that one plant, all the stage of the plants, this is bad, this is good, the leaf, and so on. As I say, it's like the face. There's no magic trick like the machine say, oh, yellow, I know, it's bad. No. They had all this picture, and first they had to label all of them. This part, this yellow part there is no good. This plant is growing this far. So tons, like, I don't know how many hours or much budget, but it's typical supervised, okay, we agree, because we don't know the parameters. I don't care if he clusters the plants in one going left, right. I mean, if you make segmentation, I want specific stuff, bad or good or healthy or not. So I decide the labels, supervised learning, so a lot of training. So yeah, so this is transfer learning. And same for school and education. The second topic was what to learn our children, what to teach, our children. And this guy, it's not me, was saying that in the end we just have to learn them, which we lose for now. It's my personal opinion because I agree with him. It's not part of the talk. It's critical sense, or to critique the data or the things that are happening, like critic sense, like to evaluate and say, oh, but that's not good. And our children I see a bit lose that, and logic. All the rest, and history and culture, I mean this part, but I mean in a big field. History and culture are important too, to be able to have this critical sense. But the rest, a lot of things we do every day, like math stuff, will be used or replaced in 10 years, he says, by machine learning. I mean, by artificial intelligence. All the automation, when I see now the process that are trying in the banks, all these apps and stuff, in the end, I mean, everything will be done, most of the thing will be done automatically. So take it into account in what you'll do. And even they say that now we are searching for data and for answer. And the next step they're trying to do is you don't need to search because the computer will know that you need this data for your business because of the analysis you do, so it will give it to you. You don't need to ask it. It's Gartner, so it's it's the biggest prediction agency in the world, I think. So by 2022, it's 3 years. Don't say it's a valid one, but I mean, they're supposedly serious. So this link to what we were saying, I mean, to the decision making. So the search engine will, when you pop up, say, okay, today you need to know this, okay? So this is the evolution of machine learning. Any more questions except for deep learning, which was not clear? Or you want to do it now? Or it's your prefer not? Which I understand.
Yeah, if someone wants to know, yes.
So he works already with one of the algorithms I didn't, because I cannot do all of them. So dimensional reductionality, which is one of the type which I didn't exemplify. I saw it. No? Oh yeah. So this one, dimensional reductionality. So it's one big ensemble of small stuff. So if you are interested, not too tired, he can give a word of explanation, apparently. So I'm not deciding, you decide. Not too tired. You can say no, don't be shy. No? You're interested? Much it will be. I see one yes, nobody else. Okay. For one guy. But you can still do it. And for me, because I'm curious what you will say. You want some slides? You need some? You have some. Even better. Okay, let's hire him for next time. Okay, thank you on my side. Sorry for the gap. And any question for me, seriously, more before he's joining?
Actually, I have a question myself. Like on the...
Oh.
So we are creating more complex models.
Yeah.
And we see everywhere, but actually at the same time, a lot of people are raising the question, okay, why don't we make them more interpretable? Like, because if you...
Yeah, I got. But it's different.
I think we are a curated audience, so we are aware of it. And even for me, like sometimes it's just too far.
No, but the problem, actually, it's a really good question. It's really a problem that we have even with our clients sometimes, because I was doing predictions before too, but you know, here. So yeah, there's one problem nowadays. I'll go back to this awful sample that I don't like. I will change the image, I don't know. It was clear, maybe it's the translation, I mean the conversion, but yeah. So yeah, there's two things. That's the one I wanted. Okay. So one other difference you have, that's why it's kind of an uneducated question, I mean, not clear question. Typically for machine learning, algorithm, typically, you can explain what's the result. I know why I draw this line and why this price is like this, and my model takes into account, as I said, the number of bedrooms, and I mean, I know all of, I can explain, explainability, why I use this model and what are the factors. Like for credit scoring, big subject, so if they use AI and they use modeling, they didn't use AI before, but they use modeling for sure. Is the bank will give you a credit for your house for what you're requesting. They will give you a model, and you're either good potential customer or bad potential. So they will do credit scoring. They use parameters for that: your previous transaction history, your revenue, your age, whatever. So your potential growth, revenue, and so on. So they will use a lot of parameters: your type of accounts, your parents, whatever. So they will use a lot of parameters to give you a credit scoring. But they are binding legally binded to be able to explain it to you why you didn't get it, if you get it. Or if you go to legislator or to court, they have to tell you, you didn't give the scoring for this reason. So you can use almost all of the, machine learning in general. The problem with deep learning is we give him we give him these parameters in these small blocks. This image that he divides and so on, and he's making the assumptions. Like he's really like intelligence. Like if it's, as I said, if it's this distance and this, so he's building a model. I'm giving him the parameters and the label data if it's good or not, and he's dividing the problems, making assumptions, making patterns out of it. And most of the time with deep learning, I don't know. I don't know what the features is extracting. Yes, it's just mathematical. And you arrive to the solution. The solution most of the time is good, but it's unexplainable by human. I do not know why. It's logic somehow, but it's so many, and maybe on this screen it's logic, but when you input 1 trillion of image, you have 1 week of computation for your model. You cannot reproduce, it's difficult to know which, it's this part of this image that completely screw my model. Maybe sometimes it happens. Or it's because of those 1,000 images on the 1 trillion that it deduced this. Basically it's a black, for most of people, even for me, the principle is you feed him with data, he will learn from it, and represent like brains, passing this one I don't pass, so on to the next one, but you cannot really say why. So you give this sometimes, and deep learning will give best results. But you give this to like my bank or to my clients, like, I have super model for scoring your customers. I'm sure with 10% more than before if it's a good customer or bad, and I validate it with the historical data. And you say, yeah, okay, why? Well, I can give you the model. Can give you, but why? No, it's just like it's impossible to know. He made some computation. The model is there. And it's a black box. You put the new customers. I'll tell you if it's the good one or bad one with a super. But you will refuse it. So, but it's not in every area. So it's not in every area. But most of the time, it's because of the type of calculation you're doing, not in general in AI. So some are what we call explainable. Some of them are not. And it's a problem for some businesses. For some, it's not. If your car has to go left or right, there are thousands of things that are happening. You don't need to know why specifically, so they use it. But if it's something you have to be able to explain or to justify, then you probably have a problem with deep learning. Good question. Good.
It's more because I know a lot of people are talking about decision making with data.
Yeah.
And the complex algorithms, and then people are questioning. Okay, like we heard that Amazon was tracking performance of employees.
Mm-hmm.
I don't think the model was very complex, but then those people were raising questions. Okay, how do you make sure that I'm more efficient than this employee or this employee?
Yeah. They might not want to explain to you, but they know. I promise you they know. This is explainable model. They take some parameters, not deep learning. They will take like, I don't know, the number of characters you type, whatever. And they know if you spend all your day in the coffee machine, there's no email sent, no stuff sent, they for sure can explain to you. And most of the time it's not so advanced. They don't want to explain. That's different. But that's another problem still. But yeah, but those kind of models are explainable. But then I understand the public saying, yeah, we should know what's happening. It's like the dynamite. It's not about the problem is not about the technology. It's about how you're going to use it. And it's the same for every innovation, improvement. It's going to be the same. I mean, we will find something that is useful for most of people. You can always use it. The scammers, this kind of Nigeria stuff that you send money or that spies you behind your computer, they use the same. It's like, okay, if you ask this and this amount and this, they analyze a lot of, I mean, it's not even, don't have to do intelligence. They do this and then they gather insights and they use it to improve it's like the weapon and the shield problem. You use the research to improve the weapon and then they improve the shield and then, so yeah, so all about use case and usage and your philosophy behind it. But that's bigger problem, let's say. Okay? I mean, so you want to, still you have the courage for him? Yeah, he was saying yes, but he left. He's the only one that said left, so that's why he was like, yes, I want to know, but he just left, so I don't want to, so you don't have to. It's like, it was already a lot to understand, to get for today, maybe unless you knew a lot already. Okay. And pizza are for?
Already there.
Already there?
Yeah.
We can eat pizza looking at the presentation.
Yeah, maybe, no, that would be, I don't know, he decides. It's very short, so okay. You still have courage?
Yeah.
I'll give you my mic. Or you prefer to do it just for this audience?
No,
Because it's also, yeah. No problem.
Just like.
yeah, I don't have
Yeah, the one. You don't have that one.
Wait.
Yeah, here.
It's not like.
This one?
Yeah, let's like this one. Yeah.
Yep.
Okay.
It's the real one, right? Yeah.
Yeah.
And I'll sit for once. Whatever.
So I had to make a case for, I was applying for a job and they said, okay, you need to create a nice dashboard and nice visualization with Tableau. And I'm like, okay, what do I use? So I took the FIFA players data set, which is available each year. So they extract the information that you have in the FIFA video game. And I was wondering, I was making some questions. I was like, okay, what is the big difference between Keylor Navas and Thibaut Courtois? And like I was wondering, is Thibaut Courtois really better than Keylor Navas? And in the FIFA dataset, what you have is different features. So you have diving, handling, kicking, positioning, reflexes. And I started comparing those in the table, like, okay, diving, we see that Navas is better at diving, Courtois is better at handling, and so on. And also like the value and the wage, and also the overall rating. So you see that overall, Courtois is better by only 2 points, but still he's better. So you could say, okay, if you take it as it is, Courtois is better. If you look at the value, say, higher value means better score in a simple way. But what I wanted to show is, okay, how could I represent all those features in a 2D representation? And that's basically what principal common analysis does, and correct me if I'm wrong.
Yeah, that's fine.
Not an expert, but basically it takes the mass of all those features and it tries to create components that explain most of the variance that we can see in the data. So, and here we don't have it, but actually out of this we get this 2D map of all the goalkeepers. So here we only have the goalkeepers because if I take all the players, Tableau is crashing, of course. And what you see is that actually Keylor Navas and Thibaut Courtois are very close to each other on this 2D map. So actually from all of this, what we get out is, they're very close to each other. So the person who was interviewing me was like, okay, but what do you get out of this? What's your insight? I said, well, if you look at the value, Thibaut Courtois is evaluated at 53 million. Navas is only at 30 million. So my recommendation would be sell Courtois, buy a better striker or a good striker, and then keep Navas in there.
Question? May I have tricky question? No. Why they are in the middle if they are so much like, they should be the crop, they should be the best one, and in your graph they are in the middle.
Sorry, I didn't understand.
You pulled all the attributes, it's all the keepers you said.
Yeah.
This part. So they should be on some, if they are the best one, they should be on, I mean, on some, on the top somewhere, I mean, on the area.
Yeah.
And here,
Center, yeah, I did the axis, this is that practice, but the center is here.
yeah, but so they are far from the center, so they should be even better goalkeepers than them.
Those ones.
Yeah.
I did.
I know, that's what I understand from your graph, so I'm just, because they are quite from the, I mean, yeah, I didn't know the center was there, but they are quite in the center, they're quite on the left, so they should be even better value, probably the, but what you did, you didn't divide by the, I mean, probably the price, I mean, the price is,
The price is not in there.
ah, you didn't put the price, ah,
No.
so the price then
No,
is inflating.
I didn't
So
pick
if the
those
center
up.
is there, then they should be better keepers, but okay. I mean, I don't know, I don't know what you draw exactly, but yeah. I know, Chibokura is on the side, so maybe, so they are probably inverted.
Yeah.
So they're probably,
Another-
so your 0 is probably here, and they're part of
There
the,
you have the axis. So you see reflex.
ah, yeah, okay, so,
And then
no, I
kicking
thought they were here because you had the labels, so they're on the side, so they are part of the best ones,
Yeah.
probably. Okay, thank you.
You're welcome. I
Sorry
hope
for
it
the-
was clear.
Sorry for the question. Okay, so you can eat. Thank you for your attention. Thank you. I hope. My mail is in the presentation. I mean, you have stuff if you have questions, or if just